In 2015, astronomers pointed the Kepler Space Telescope at a star named KIC 8462852, located nearly 1,500 light-years away in the constellation Cygnus. What they saw defied conventional astrophysics. The star's light was plunging, dropping by up to 22% for days or weeks at a time, with no predictable pattern. Planets or dust clouds don't block that much light. That discrepancy fueled an extraordinary hypothesis. Astrophysicist Edward Schmidt wanted to see if Tabby's star was truly alone. He ran an algorithm through the Northern Sky Variable Survey, scanning 14 million objects to look for anything exhibiting those same bizarre light fluctuations. He found 21 matching candidates. 15 of these stars were slow dippers, dimming at rates similar to our original anomaly, and 6 were rapid dippers, exhibiting even more extreme variability. Finding multiple stars with similar erratic behavior across entirely different spectral classes and masses pointed away from an alien megastructure. The sheer variance means these dimming events are almost certainly a natural mechanism, likely massive irregular clouds of dust or fragmented comets caught in the orbits of these stars. When we look deep into the Milky Way, we don't see any confirmed signs of stellar engineering. The cosmos appears completely quiet. But an empty sky doesn't dictate that stellar megastructures defy the laws of physics. Our telescopes haven't spotted a Dyson sphere yet, but mathematical models suggest humanity is actively on track to build one. In 1964, Nikolai Kardashev proposed a scale classifying societies by energy consumption. A Type 1 society harnesses all its home planet's energy. A Type 2 society harnesses its star's total output. Right now, humanity sits at an intermediate status, roughly Type 0.72. To plot when we might bridge the gap to Type 1, researchers at NASA's Jet Propulsion Laboratory developed the Civilization Development Index. This mathematical model tracks the transition to a stellar society using 4 distinct metrics. This chart tracks the total global energy supply generated from clean sources over the last 3 decades. You can see the steady baseline of nuclear power, but the crucial metric is the rapid, exponential upward curve of renewable energy adoption. By extending these exact historical growth rates into the future, the researchers calculated a specific timeline. Following this energy curve, researchers project humanity will reach full Type 1 status, harnessing planetary-scale power by the year 2021. Transitioning to Type 2 introduces a massive computational hurdle. The CDI's second metric is information processing. Managing a stellar megastructure requires an astronomical amount of data, likely handled by a Matryoshka brain, a theoretical supercomputer built in layers around a star to draw power directly from its radiation. Processing that much data generates immense heat. To survive close orbit around a star, these computers must be built from highly advanced thermal-resistant materials, operating near the absolute limits of thermodynamics. Research suggests carbon, configured as diamond, is one of the few materials capable of withstanding these forces. There is also the matter of construction mass. A Dyson swarm or a Matryoshka brain requires a staggering amount of physical material. If we dismantled every resource on Earth, we still wouldn't have enough mass to build it. This graph tracks humanity's construction mass index over time. Notice how the line, tracing our historical baseline in the year 2000, spikes dramatically as we project forward to 2100. This relies on our ability to leave Earth and extract materials from the asteroid belt. To achieve this scale, a species must outgrow its home world and evolve into a fully interplanetary industrial engine. To run that massive industrial engine, you need the fourth metric, population. Earth has a strict ecological carrying capacity, but by expanding into orbital habitats and lunar bases, a species increases its living space, allowing for the sheer population size needed to construct and sustain stellar-scale architecture. This graph maps the Civilization Development Index, synthesizing energy, information, mass, and population. The curve intersects the Type 1 threshold near 2270. If technological growth continues, the trajectory stabilizes, crossing the Type 2 threshold between 3300 and 3500. This timeline projects humanity reaching the Type 2 threshold and achieving stellar-scale infrastructure in less than 1,500 years. We now face a profound contradiction. Our models suggest a Dyson swarm is realizable, yet when we scan stars like KIC 8462852, we find nothing but dust. This discrepancy points to the Great Filter. This theory proposes that somewhere between harnessing a planet's energy and capturing a star's output, civilizations hit a massive existential bottleneck. It could be ecological collapse, technological self-destruction, or simply an inability to sustain social cohesion across planets. The fact that we don't see alien megastructures doesn't violate the physics. Instead, it serves as a warning. The centuries required to transition from a planetary to a stellar society are volatile, and our progression toward that destination is not guaranteed. Thermodynamic limits, construction mass scaling, and historical energy trends all align. If we successfully navigate the existential risks of the next few centuries and sustain our integration, a Dyson swarm is a realizable goal. Rather than staring into deep space and feeling disappointed by the quiet, we should look closely at the current era. For humanity, the cosmic silence is an invitation. Humanity is currently laying the planetary groundwork to become the very architects of the cosmos we've been looking for.